This is a brief introduction to statistical power. Let's review some of the errors that we can make in statistics. You might remember that there was a type 1 error, our alpha error. Typically, we say that we're going to allow ourselves to reject the null hypothesis 5% of the time when we shouldn't reject it. And so that means that the type 1 error is seeing a relationship that's not really there. We might conclude that something's correlated with each other, but it's not. And we, by setting the alpha level, we get to choose how often we make this type 1 error. So that's the type 1 error, but we're interested in type 2 error when we talk about power. Type 2 error is when there's a relationship between two variables, and they're correlated, but we don't detect it. We don't get the right data. We don't get enough data. We measure it wrong. We randomly get a sample that doesn't indicate what's in the population, something like that. That is a type 2 error. And so the type 2 error is when we conclude that we don't know if there's a relationship when there really is. When we say, I don't know. But we should have been able to see that relationship if we had measured everything in the whole population. So this type 2 error is also called beta error. And so it's going to be, our beta error is retaining the null hypothesis when we should reject it. Now obviously, we don't want to make beta errors. We don't want to study something that's real and come to the conclusion, I don't know if it's real or not. That's really discouraging. We want to come to the conclusion that, oh yeah, here's evidence that it is real. So we want to avoid making beta error. Now, how does this relate to power? Power is defined as a probability that a study will detect a difference or relationship between two variables if such a difference or relationship is real. So if we're looking at a correlation between extroversion and positive emotions, if that really exists, we want the power to detect it. And the value of power can go anywhere from 0, a 0% of detecting the relationship, to 1, 100% chance. For example, if we only measured 2 people, we might not see the correlation. Our power would be very low, but if we measured thousands and thousands of people, we're much more likely to detect that relationship. Now, it turns out that tests in the social sciences and organizational sciences with power of more than 0.80 are somewhat rare. They're becoming more and more common as people are becoming aware of the importance of power. But they are becoming, in the past you could see tests with often that only had power of around 50%, which is pretty discouraging because that means you run a complex study, and if the phenomenon you're studying is real, there's only about a 50% chance of detecting it. Now the relationship between power and beta error, the type 2 error, is that they're inversely related. Power is 1 minus the fraction of beta errors that you make. Another way of saying this is that the two have to add up to 100%. For example, if we mistakenly retain the null hypothesis 10% of the time when we should reject it, so if we make a type 2 error 10% of the time, the power of the test is 100% minus 10%, 90%. So the higher the power, the better. The higher the power, the fewer beta errors we're making. That's the definition of power and beta errors. Now, you might have noticed that on these slides, we've got Mr. Bean here. We'll come back to that. Now, what's the relationship between power and effect size? Well, power is a measure of the sensitivity of a test to detect some real effect, some real relationship. And so the greater the effect size, and you might want to watch the video on that if you're not familiar with the concept of effect size, but typically effect sizes are either R's or D's. The more power, the greater the effect size, the easier it is to detect it, so the greater the power we have. For example, with a correlation of 0.30 between a personality trait and productivity is easier to detect than if the correlation was only 0.12. That makes sense. It's bigger. It's having a bigger effect. We can detect that more easily. If it's only 0.12, it's a lot smaller. It's harder to detect. We can miss it more easily. So the question is, what are some ways to increase power? And the way that we can remember this is with the acronym BEAN. So that's why Mr. Bean has been a theme of this presentation. And that kind of the little rule of thumb is, with BEAN, if you want to change the B, you change the others. So if we want to change our beta errors, how many beta errors we make, which is the opposite of power, so we want to make fewer beta errors in order to have higher power, we need to be concerned about the effect size, because the greater the effect size, the greater the power to detect it. We can also be concerned about our alpha level, the probability of falsely rejecting our null hypothesis, the probability of making a type 1 error, and we get to determine this. We almost always choose 0.05, but if you make the test less stringent and raise the alpha error, like from 0.05 to 0.10, that increases our power, because we don't have to have such narrow criteria for rejecting the null hypothesis. So we can get power by raising the alpha level, which means that we'll make fewer beta errors if we allow ourselves to make more type 1 errors. So conversely, if we make the alpha level more stringent, we'll make fewer type 1 errors, but we'll make more type 2 errors. They counterbalance each other. Now, the best way to increase power is the sample size, and increasing n increases the power. That means that if you have a larger sample size, you're going to be more sure of your results, and it's easy. You're more likely to find a correlation to be significant with a larger sample size. So that's the best way of doing it. Now, one of the things that we can use to figure out one of the applications of power is it can help you decide what the math behind this can help you decide what sample size you need. And so to do this, you can go to a sample size calculator, and there's quite a few of them on the web. I've got one here. Let me click this, and we will go to it. Here is a sample size calculator from the University of California at San Francisco, and we can use sample size calculators based on the alpha and beta levels that we want. The alphas are type 1 error, and so, for example, we pretty much always want alpha to be 0.05, and suppose we want to measure, we only want to have 20% beta error, or we say, oh no, that's too much. Let's say we only want 10% beta error. We only want to miss the relationship 10% of the time, and we're going to study some correlation. We have to make an estimation of the correlation. So like maybe we want to test the relationship between work performance and conscientiousness, and typically that has a correlation of about 0.15. We enter the how often we're allowing ourselves to make a type 1 error, how often we're allowing ourselves to make a type 2 error, and the estimated correlation. We press calculate, and it gives us down here the correlation that, or the sample size that we need, 463. You might say, oh man, there's no way I'm going to get 463 participants. Let's make it less stringent. Let's go, let's say we can make 25% beta error. How would that be? So we change that to 25%, and it goes down to 307. And you say, oh, I think I can get 307 of my Facebook friends to fill out a survey. I'll go with that. So this is a way that you can estimate what sample size you need to have the power to detect the effect that you want. And if we were using D categories of correlation coefficients, we would use a sample size calculator for D's rather than R's. And they're pretty easy to find on the web. You just Google around and you'll find them.